All right, so let's take a look at this region. All right, the region we are thinking about is, of course, this part that looks sort of triangular here, right? And this point, by the way, was 1, 1, because that's where the x squared and negative x plus 2 intersect with each other. All right, and so now, okay, now what's going to happen? We are going to use y as the variable of integration. Variable of integration. All right, so what does that mean? Well, so try to think of y going from 0 to 1. For each y, I have, let's say this is, let's say y is like 1/2. So this is what I am trying to integrate. Now, the idea of integration, remember, it's a continuous version of addition or accumulation. So now I'm saying for each y, where y goes from 0 to 1. This time, I am not going this way. I'm going this way. Okay, I hope it's clear. For each y between 0 and 1, okay, I have to integrate the length of this red segment. Okay, so y goes from the lower end, which is right here, right? Y is equal to x squared. In other words, y goes from the point representing this to a point representing that. But the thing is, I mean, I'm looking for the x coordinates of this point, right? And the next coordinate of this. So what I have to do, and here's the important part, okay? Each of these needs to be solved for x. So x is equal to what with respect to y? Because now y is considered an independent variable. All right, so for this, I solve this, and of course, x is plus or minus the square root of y, but since x is positive here, I will just take the square root of y, the positive square root of y, and that's this point, okay? In other words, when y is given, let's say 0.5, now this point is the square root of y, which is my x coordinate here, right? And then from this, of course, x is simply negative y plus 2, okay? I just solved this for y, and that's this point here. And so now this is the lower limit. This is the upper limit for the y values. Sorry, for the x values. Okay, x goes from, so I should say for each y between 0 and 1, x goes from square root of y, I should say, again, for each y where y is between 0 and 1. X goes from square root of y to negative y plus 2. Okay, and the those are the upper and lower limits. So in other words, the graph goes from here to here, here to here, here to here for each y. So I am now integrating with respect to y, meaning I am adding up all these red line segments in a continuous fashion, and my area then is going to be from 0 to 1, as y goes from 0 to 1 of this minus that. dy, okay, so this is with respect to y. Now it looks very different from what we did before. And we did not have to, in this case, separate this into two regions like the red and the blue regions, okay? Because in all of at every point y between 0 and 1, the length goes from this to this, which is from the lower function of x is equal to the square root of y to the upper limit, which is where x is equal to negative y plus 2. All right, so this is the higher of the two values, and then this is the lower of the two values, not x values. All right, and then if you calculate this, you will get the area of the entire region. Watch, okay, so this is negative y squared over 2 plus 2y. And then now this is, of course, y to the 1/2 power. So this becomes 2/3, y 3/2, right? And then just evaluate from 0 to 1. So when you plug in 1, you get 1/2, and then 2 minus 2/3. Of course, if you plug in 0, you just get 0, right? So what is that? This part is 3/2, right? And then you subtract 2/3 from that. That's 6, right? And then this is 9 minus 4, and that is 5/6. And that is what we found last time, okay? So this is one way to do this kind of calculation and this kind of an integration. All right, so now let's do another example on finding the region, finding the area of the region, okay? This time, here's the question: find the area A between y is equal to x and y is the cube root of x. Okay, now sometimes a graph may not be given to you. You may have to figure out the graph. And you know, in this case, you are not given the graph, you're just given two functions. So you have to either imagine or you have to draw accurately the picture so you know the endpoints and you can figure out what they're looking for, right? The area between these two functions. And so maybe you can just go ahead and try to graph this and then come back and see if you get the right graph, right? I'll go ahead and graph this. The first one is easy, straight line. So that would go like that, right? And then the second one, the x cubed, of course, that is more complicated. And basically, it kind of goes like this. So should I make this into, yeah, let's call this 1, 1. Yeah. By the way, 1, 1 is, of course, in here and in here, right? The point 1, 1, it satisfies this equation and this equation. So that's an intersection. And 0, 0 as well. And -1, -1 as well. Okay, so you should know maybe the y, the cube root of y, or the cube root of x would look like this. Oh, it does not. Looks like that. So let's go ahead and erase this. That is my bad. That's the cube function, right? The cube root function is going to be the inverse of that. So it'll be more like, oh, okay, I did not mean that. It'll be more like this. It goes through 1, 1 and gets down to here, 0, 0, and then goes in here. Okay, so this is the cube root of x, and this is x. All right, looks like the area between these two comes in two parts, this part and this part. Okay, and you know that there's a symmetry involved in this, right? And so anytime you can use symmetry, I highly encourage you, I almost urge you to use any symmetry possible, because that would make your calculations much easier. In fact, in this case, you're supposed to find the sum of this area and this area. Let's call this area 1 and area 2. So what you're trying to find is this, okay? But you can easily see by symmetry that the area is going to be 2 times the area 1, which is what I call this one, okay? So the area 1 can be found. Oh, by the way, I guess I should make sure that this is correct and that I do have these 3 points and no more, right? So I can just find the intersection. Find the intersections, because there are 3 points of intersection. X can be considered equal to that, right? How do you find the answers here? You can cube both sides. You get x cubed is equal to x, and x cubed minus x is equal to 0. And by the way, you don't want to divide anything by x yet, because x could be 0, and dividing by 0 is a problem. But you can always do this, cube both sides, and then you can factor x, and you will see, I mean, this is a cubic equation, right? And so this makes it clear that you only have exactly 3 points of intersection. And you see all of them. 1 here, 0 here, and -1, right? So the area enclosed by or bounded by these 2 functions is exactly a1 and a2. And now we are to find twice a1. So let's say a1 is going to be the integral from 0 to 1, okay, of what? Well, over here, the upper limit is x cubed, or the cube root of x. And then the lower function is x. So you simply do that. And let's try to figure this out. This is, again, adding 1 to this. So that would be 4/3. Take the reciprocal, 3/4, x to the 4/3, minus 1/2 x squared. Evaluate this from 0 to 1, and you get 3/4 minus 1/2, and of course, minus 0 at the end. That's 4 in the denominator, 3 minus 2. And so the answer is 1/4, right? Of course, a is twice as much as that, so this will be 1/2. And that is your answer. Okay, so that's using x as your independent variable and x as your variable of integration. But we have also learned to do this using y, right? So let's go ahead and do that too. Now, again, if you took x as your independent variable, you are integrating in this fashion. All these lines here, you know, you have lower limit of x to the higher limit of x to the 1/3 power. This time, can you see what you're doing? For each y, I am taking the point from here to here. So I have to find this x value, the lower, and then this x value, the higher one. Remember, this function is y is equal to the cube root of x, and this is y is equal to x, right? So it is necessary to rewrite these as x is equal to y. See, the thing is now, because we want y to be the independent variable, we have to solve both of these equations for x. So here, x is what? If y is the 3rd root of x, then x is y cubed. Okay, so that's just the inverse function. So for each y, x goes from y cubed to x. So a1 is going to be, again, y going from 0 to 1. And then the higher of the 2 functions, of the higher of the 2 functions is, see, higher just means the right endpoint, okay, of these black segments. Okay, the right endpoint is always going to be the point on x equals y, and then the lower limit of x is the other one, which is y cubed, right? So you evaluate this. You evaluate this integral with respect to y, and you should get the same answer, which was 1/4, and doubling it, you should get 1/2. Let's go ahead and do that. This will give you y squared over 2 minus y to the 4th over 2. Evaluating this from 0 to 1, you have 1/2 minus 1/4 minus 0 minus 0, of course. And this is 1/4, as before. So a is 2 times a1, which is 1/2. And that is still the same answer. You should always be happy when you get the answer you wanted to get. Okay. If this happens to be 1/2 or not 1/2, then you are in some sort of a dilemma. And then you may want to go over either this answer or this answer, because they have to be the same, right? Regardless of if you take the integral with respect to x or with respect to y, the area itself is the same. So the value of the function or the value of the integral should be the same, right? Whether you use x or y as the independent variable, the variable of integration. And now you got the right answer, so you can sleep in peace. All right, so get used to this. I know this makes many students uncomfortable because you have really not used y as the variable of anything, independent variable. But many times, many regions do require you to integrate with respect to y. So it is good to stretch your mind and imagination and to be able to use y as your variable of integration.